Okay, so today we'll talk about DCT and DST, Discrete Cosine Transform. I think this is not the right file. Go back. This one. It is, okay. So we'll talk about Discrete Cosine Transform and Discrete Sine Transform. And we'll look at first the derivation that we started last time, how to derive the Discrete Cosine Transform from the Discrete Fourier Transform, the concept of basis functions, and then we'll talk more about the compaction power of DCT with some examples. And this will be an introduction for a later on subject, which is the compression and image compression and video compression, which is a very important component of these standards, is the transform and the compaction power of the transform. And in most of the standards, DCT is the underlying transform for these compression standards. So as we showed last time, if we can do certain engineered extension of our f of m and n, in this case around the y-axis, around the x-axis, and around the origin, and then we shift the axis so it can be centered here. Then now we can start to write the forward transform equation to compute the discrete Fourier transform for this extended f. And we did this last time, where now if you look at the window of this extended image, it doesn't really start from 0 anymore in both directions. It starts from negative m and negative n all the way to m minus 1 and n minus 1 in both directions. And then we have the shift by half a pixel for the axes accounted for in here. And we can split this region of support based on the limits on the two sums. So this one here, when both small m and small n are the negative. This is when small m is negative and small n is positive or 0. And in here, when both are, so when m is positive or 0. There was an error, and thanks for somebody pointed out this, and on Tuesday it was capital N. That's wrong. It should be small n between negative n and negative 1 in this case. And then this is the one where we have both in the positive or equal to a 0. And then what we did, we started really to compute just go through the arithmetic, the operations, to calculate the discrete Fourier transform by trying to put it in a certain form where we have the summation over positive or 0 indices m and n, and we take into account the facts that are in the first slide, how we did the extension. So this is one for the first term in our 4-term calculations. And we do the same thing for the second. A2 is a change of variable, and then we take advantage of our extension, and then we write it in this form. And we keep doing that for all 4 terms, A1, A2, A3, and A4. And once we have all of them in here, then you can see from these terms, we have the first parts, the summation limit, as well as the f and n are common across the 4 terms. And then if we can take these as common factor, what we'll be left with will be these complex exponents. With an observation here, which is, you can look at the m term here, the same thing for the n term. Then this is nothing but really a product of 2 each one of them is a function of n, small n, right? And if you look more carefully at each term in here, using the Euler's formula, then this is really nothing but what? If you divide this by 2, then this is really 2 cosine, right? So this one here is 2 cosine, whatever we have in this exponent. And then here, the same thing in here. This is 2 cosine, whatever we have in the exponent, which is a function of n. And then we end up with this definition for this Fourier transform. So when we have this extension around the y-axis, around the x-axis, around the origin, then what we have is discrete cosine transpose. And if we, this is the slide where we had a definition of the discrete cosine transform that we concluded with last time. Then this is the forward definition. This is the inverse definition. As I mentioned, there are some variations among different definitions online, but this is the one that we'll be following. And then the most important concept in here is that the basis functions for the cosine are really cosine. That's already the real part of the basis function of what we had for the Fourier transform, which was the complex exponents. And we'll study in more detail in a few slides what that means. So some examples for you, just to look at most of these examples, just to start to kind of get you around, just to think about the compaction power of these transform and DCT case. Compaction power meaning that we compact the energy in fewer number of coefficients. The number is much smaller than the number of pixels that we started with in the image. And you can see in here for this image in here on the left-hand side, the DCT is on the right-hand side. This is the 0 and 0 for the image, for the DCT. So this is the component DCT of 0 and 0. That's the DC value. And then this is the highest coefficient, meaning the coefficient with the highest frequency in both horizontal and vertical. And you can see the majority in here are really zeros, or very close to a 0. So you can see the compaction power of this algorithm as we'll study this more. There are some different examples of the details, and you can see in here they are already showing up. You can see maybe, I don't know how good you can see it in your. This is basically you have some non-zero coefficient. Here is mostly zeros. You can see it's almost one fourth of the coefficients are non-zero. The rest 75% are zeros. That's a big compaction. For coding. And there are some examples. We apply block based for DCTs, meaning that we take 8 by 8 from the image, 8 by 8 blocks, and for every 8 by 8 we apply an 8 by 8 DCT transform, and we plot that. We plot the magnitude basically as they are. So let's look at this example here, and this will really get us into to think more about compression and coding and compaction. So imagine that I have this pipeline where I take an image and then I apply a transform, in this case DCT, and then I have some masking and that masking it's nothing but to tell me which coefficient in the DCT space, this domain, I would like to zero out, and then I apply inverse DCT. I have my image I2, and now I want to compare I1 or I and I2. So let's take, this is just an 8 by 8 block from one of the images that we have. I think this one from Melina image. So these are intensity coefficient, this between 0 and 255, that 8-bit image, Lena. And these are one of the 8 by 8 blocks in a uniform area, and you can tell this is a uniform area because the intensity values are very close to each other. They are all in the 200 region, actually the upper 200, yeah, so they're really 230 plus to 255. So it really almost a very uniform 8 by 8 block. So now, and we'll have another example where I have another block that was taken from an area where is not very uniform or as uniform as this one. And we'll see basically what the impact on this when we do masking. So the first thing, I take the image I. This is, forget about the entire image. I just take 8 by 8 block. Here is one of the 8 by 8 blocks. I call it I. And now I apply DCT to it. The output is B. And now this is the DC value. right? And then this one is the next DC. This is the next one. We do a zigzag, and we'll talk about that in a minute. So this is the DCT coefficient with the highest frequency. So you can see basically as you go from the upper left corner to the lower right corner, we're really increasing in the frequency axis, but at the same time you can see the magnitude-wise in terms of magnitude of the DCT coefficients, we're really going down. That means the higher frequency is zero, and to fit this is the fact that our image to start with, our 8x8 image in here is more or less is uniform. So there's not really much of variation. So if you look at most of the high frequency content, which is this half, 32 of these coefficients are less than 1 in terms of magnitude. Compare that to the DC, which is in the 1954 range. So now our masking in here, our masking meaning which ones I want to zero out. Imagine that our masking in this specific case for this example, for this slide, it's all ones, meaning that I multiply 1 by 1 point-wise multiplication, where I multiply every DCT coefficient by 1. So basically B and B2 are equal, right? So B and B2 are equal in this case. So now I have B2, which is the same as B. And now I want to apply an inverse DCT, and then to get I2, and here is I2. And then you can basically I with 2, then unless you have rounding error, they should be equal to each other, right? So so I and I2, they are equal to each other. So you can see in here, this is the conservation of energy. We didn't really lose any of the energy in the image because we haven't really done any quantization or any zeroing for our DCT coefficients. The mask basically passed everything as it is in the DCT coefficient. So that's basically a simple that can get your image back if your mask is all ones. So next, the entire image for every single block, all the 8x8 blocks. And then you compute the PSNR between the two images, then the PSNR will be infinity because the error is equal to a 0, or very close to a 0. It's in reality, in your next homework, if you do this, then if you do this, then it will be 10 to the power of negative 16 or something of that order. So it's very, very close to a 0 because there might be some small rounding errors in the computation. So then the next thing, we'll repeat the same experiment, but now our masking is more strict, meaning that our masking in this case is operating in a way where we will only, this mask will only pass through the first 10 coefficient. And the 10 coefficients are defined by this red triangle in here. So meaning that our mask, and we'll understand why this mask is coming from where, but for now, just assume that somebody told you that whenever you have an 8x8 DCT coefficient, then the DCT operation, then from the 64 DCT coefficients, you will pass only through the first 10 coefficients, including the DC. So you have one DC and then the following 9 AC coefficients. But then everything else is 0. You can see in here, all of them are really zeros. And we do the same operation as before. So we have B2, we apply inverse DCT. And now this is the resulting one. So I2 and I, you can compare these with each other. And you can see basically they are not identical. Because why? Because we lost information by zeroing out 54 of these coefficients, right? But if you think about the number, the intensity values, the individual ones, this was 246, this is 247, this was 242, this is 245, 250, 251, and so on, 241, 245. So that's really kind of one or two, maybe more, maybe less variations in intensity values, right? And the reason is this loss of information is not because DCT, is really because of the mask that really got rid of 54 of the 64 coefficients for every single 8 by 8 block, right? So if you apply that, so now the image on the left hand side is our original image, and we took every 8 by 8 block DCT, keep the first 10 DCT coefficient defined by a triangle or a zigzag tracing, and then zero out everything else, and then apply the inverse, do the same operation for every single 8 by 8 DCT coefficient. And then this is the image on the left-hand side, the right-hand side. So this is only decoding or taking account only for every 8 by 8 block, right? Not for the entire image. And then if you look at the PSNR is 28, but we know by now the PSNR doesn't really tell you much. But in here, if you really compare these two images, there's very, very slight variations if you can even perceive them. If you do the same operation, so now there's 10 DCT, right? So one way to think about it, I'm only keeping 10 out of 64. Now let's move on, and now I want to do the same process, but now I want to keep 25 DCT coefficient. So my triangle, the red one, is just bigger now, but I'm really keeping 25 from the upper left corner. That's basically I'm keeping the DC plus the next 24 AC DCT coefficients, and I'm throwing away the remaining coefficient for every single 8 by 8 block. And now you see the PSNR improved from 28 or 29 to 35 dB, so it was a bit of improvement. But at the same time, in terms of quality, it's really difficult to differentiate between these two images. I mean, this one's in here. You may notice some differences you have on your computer in terms of sharpness, especially around the text region. Look at around the text, the edges around the text. You can see there is the one on the left-hand side is much sharper, not much, is sharper than the one on the right-hand side. And this one, I don't really differentiate between these two images. Even text-wise, it's very difficult to differentiate. And then we zoomed in to see basically what that means. So the one on the left-hand side, this is a zoomed in block of the I2 when we kept 10 DCT coefficient. And then the one on the right-hand side, this is the zoomed in same location of I2 and I2 when we keep the 25 DCT coefficient. And you can see in here, there is really a difference. Look at the marble as a text compared to this one here. There's quite a bit of loss on the one on the left-hand side. Look at the edges in here. So that's basically what I was referring to and saying you cannot really observe something on the one on the 25 DCT, but you can observe a little bit about blurriness and clarity in the text in the 10 DCT. Okay, Max, good question. As I mentioned before, is just basically the PSNR. So the question is, why do we report PSNR if it never really tells us much about how the image looks? It really doesn't really tell us about how we perceive the image, right? And remember, PSNR, it doesn't really tell you these slight variations. In general, you have these band. If PSNR is below like certain range, let's say below 25 or 20, and then between 20 and 40, and then above 40, or above 35. These you can say basically it can tell you, but the slight differences, as we saw before, is not really as good as the other ones that we studied before. Why do we report it in here? It's just to basically, even for the slightest differences between the two images and the text, PSNR is capturing those because it's just comparing 1-to-1 pixel. But definitely, if we can use this SIM for a better captioning of the two. I would argue, I haven't calculated this, but I would argue the difference in SSIM between these two images will be less than the differences between the two PSNR, meaning that the PSNR jumped from 28 to 30 something to 35. I would say the jump in the SSIM will be much less than this jump in here. Did I answer the question? Okay, thanks. So so the point in here is that um, e even with keeping 25 or even keeping actually 10 out of the 64 DCT coefficients, we get really an overall, because on the left, the perceived quality is reasonable. With increasing by 15 more DCT coefficients, then you have this quality on the right-hand side. So now you can start to think about this whole compression and coding and streaming. How do we decide, right? Imagine that you have, and we'll talk about this in much more detail. We'll talk about image coding, but just to give you a teaser, because it's really based to some extent on what we study today. So if you are streaming on YouTube or Netflix or one of these content providers, and then you have two connections, two users. One is really using really a very bad net connection, meaning that the end-to-end bandwidth has issues, either bandwidth or jitter. There is something in the network, and the other one is fine, of high quality. So if you want to stream the content to both of them, then now you have to decide basically how to do this. Now you have a video that runs at 30 frames per second. All right. So every 1 over 30 of a second, you have 1 frame. Times 5 for TV, especially 25 frames per second, but let's say 30 frames per second for digital videos. So now the question is, where do you really, you have to pay the price about the low quality end-to-end network that one of the users have. So the one with the good quality network, it has a high bandwidth. There's no issue. You can really have high definition, compress it, send it. All right. And the second one, if you do the same, there will be an issue where some of these frames will be dropped in between, or even they are delivered, but they are delivered basically with a variation in time between them. We call it a jitter. So you receive in the first 1 second, you receive 30 frames, and then the next 2 seconds, nothing. And then the next third or fourth second, you have 5 frames or 10 frames. So now you have these variations in the frame rate. Or you can say, okay, I want to be smart about it. I really want to keep the frame rate as it is, but I want to reduce the quality in every frame. So I want to really apply a bitrate reduction on my compression at the server, where now I will apply a very severe compression where I say for every 8x8 DCT coefficients, I will only pass on the DC value, for example. So that will give you a certain bitrate, right? And then the next strategy, maybe I will pass on the first 10 DCT coefficient in every 8x8 blocks, or the next one is 25. So now you have this quality of service, right? Profiles. So one of them will say you can vary the spatial quality, meaning that your DCT coefficient, you can start to decide how many you want to mask out, how many you want to throw out, or you can say I want to skip every other frame, right? So now you have temporal decision that reduce the quality. So there is scalability in the temporal case, or there is scalability in the spatial domain. And now that will basically get you into this kind of bitrate controllers. So a bitrate controller in streaming technology is basically is an algorithm that will take into account the device capability that the user is using, the end-to-end network quality in terms of bandwidth, in terms of jitter, in terms of delay, and then look at the content itself, the original content, and then it computes basically what would be the best operation parameters in terms of frame rate, in terms of spatial. Now, the question is, which one is better? Is it really to change the frame rate or to change the spatial? So now, from a human vision system, you don't really want to vary the frame rate much. You want to have a consistency in the frame rate. It's very annoying when you have 30 frames per second, and then the next few minutes you have 10 frames per second rate, and then you have 20. So variation in that frame rate, because the motion perception, it is very annoying to the human vision system. So instead, I want to really have some spatial variation. That's why sometimes when you look at if you provide provider or you look at YouTube even normally normal days, sometimes you see basically the quality is really varying, and you see sometimes there's a very blockiness effect in the video for a few seconds, and then that improves with time. That's exactly what's happening for this. They are really pushing the frames without really changing the frame rate, but some of these frames they have much less content because they really didn't pass on the majority of the DCT coefficient in every block. It's more complicated than that, but that's really the basic idea, the basic concept. Once you go to compression and look at the standards that they are applying nowadays, then we can really have a better understanding of what's happening. But really, at the end of the day, it really boils down to what we're talking about, which is this 8x8 64 DCT coefficient, carry the information about that block, how many of those you want to sacrifice, and network parameters. But we'll talk more about those later on. So we'll study a little bit, a few minutes about the basis functions, and which we cover here. But I think the best way to look at it is just understand what is, as a refresher, for some of you who haven't seen this before, just to look at the discrete cosine transform. So this is the one-dimensional discrete cosine transform. Forget about the scaling in here. So you have summation over small m, you have the signal f of m, and then you have the cosine, right? So now the cosine, if you look at the inverse DCT, this one here, remember when we have the Fourier series, the discrete Fourier series expansion, we can really write f of m or f of n or f of m and n as really is a function of these harmonics, right? So you have a different scale in terms of the frequency and scale is the magnitude, and then you sum them all together, it gives you an approximation of our f of mn. So in that Fourier, we had the complex exponents. In here, we have the cosine, right? So one example, if our capital M is 8, so that's the dimension, the window is 8. In our image terminology, we say 8x8. So if it's M is 8 for this specific example, let's look at what we are claiming is this f of m, I can write it as the sum of 8 cosines. Each of these 8 cosine has a certain scaling in front of it, which is the DCT coefficient, f sub c of k, and then some scaling in here that has to do with the frequency in the cosine, right? So now what we need to look at, what does that mean? So the scaling in here is granted, but let's really look at what's really happening to the basis function, the cosine, as we vary this k from 0 to 8 in this case, or from 0 to 7 in this case, which is m minus 1. 8 minus 1 is 7. So now the first one, the first cosine, when you have k is equal to a 0, this is really what the cosine of 0 would look like. And here we're just plotting basically how the amplitude is all ones at every single one of these sample between 1 and 8. That means basically we have a DC in here. So it's really capturing the average, right? You can think of this as really the DC or the average in my 8x8 blocks, or the average in my 8 length sequence in the 1D case. And then as I'm having k equal to a 1, for example, in here, then what I have in here is really half cycle, right? Because k in here is 1, and then I have the half in here. So I'm having a half cycle of this cosine, right? And then I have k of equal to a 2, then I have a full cycle of my cosine within 1 to 8. Then as I have k of 2 or 3, then I have 1.5 cycle. K equals to 4, I have 2 of them. So in a way, what we are really saying, and then K7, we have all 4 of them. So what we're saying is, in each one of these components, in plain English, in a very simplified way, the first coefficient, when k equal to a 0, that means our f sub c of 0 contains the DC values in the signal. Now, f of c when k equal to a 1 is basically the scaling of how much we have half-cycle variation in our signal, and so on. And then we have k equal to 4, for example. We have f sub c of 4. It really gives us how much variation in the signal that we have with 2 full cycles. What kind of frequency content in the signal that has these 2 full cycles within our window of 8, and so on. So you can see that this is the basis functions. You can think of it as we have 8 dimensions, and then we have the signal, and then we are projecting the signal into this new 8 dimension, and we are recapturing how much basically these projections are, and these projections are nothing but the DCT coefficients. And that's basically what you can interpret basis functions. Now this is the 1D case. If we apply this to 2D, then it's the same concept. You can think of this as going horizontally or going vertically. So if I have 2 by 2 DCT basis function, meaning I have really horizontal I'm going between 0 and 1, vertical I'm going between 0 and 1. So the first cosine of 0 times cosine of 0, right? We have k and l now we have. So basically what, let me go back here. These 2 by 2 basis functions are these ones in here, right? So now we are looking at k and l, right? So when both of them are 0, then cosine over 0 is really a 1. So basically I have a uniform. If one of them is a 0, the other one is 1, then I have variation in one direction, but not the other direction. And that's really what's happening in here. This is when both of them are 0. This one is really capturing how much you have this frequency content that being captured horizontally, meaning that you have a vertical line. That means that you're really horizontally having these variations in the frequency content. And this is the other way around vertically. And this one is doing both horizontally and vertically as well. So you can see this is the 2 by 2. The FC of 0 and 0 coefficient in here is really capturing the DC. And this one here, for example, is capturing the variation in that my 2 by 2 block of the image that has variation in both horizontal and vertical this way. As we go to 4 by 4, it becomes more interesting, because now what you should really think about is in the 4 by 4, we are capturing more variation in the content. If imagine if my whole image is uniform, right? Then it really doesn't really matter. I'm using 4 by 4 or I'm using 2 by 2 or anything else, because all what matters is the DC value. Everything else in here will be a 0, right? So there's no variation. But now in natural images, usually when you have a 2 by 2 image or 2 by 2 block, the probability that you have quite a bit of variation is really, really small. So there's not really much to be represented using these coefficients in here. However, if you go to a 4 by 4, then now I have higher probability, higher chances that I have quite a bit of texture variation in my image, that these coefficients in here, they will capture that information, right? This variation, this frequency content, all of these, right? All of them. So you can see now there is this kind of dilemma: do I keep it very small or very large, and how much is large, right? So, and here is 4 by 4, and then you go to 8 by 8, which has been 8 by 8 has been since probably since the 90s, since JPEG, the first JPEG standard was issued. It has been kind of the standard until like 2 years back, maybe 5 years ago, when we started to move into 16 by 16, 32 by 32, and actually there is 64 by 64, because the computation power we have now on our device is much, much more powerful than 20 years ago. So you can see this is 8 by 8. All what we are plotting here is this the basis functions, the cosine times the cosine. This is 16 by 16. See that this is, of course, I mean, this is really zoomed out to put all of them together into one image, but there are quite the details if you zoom into this one. So now the question that we have is, So now we understand the basis function concept. We understand basically the dimensionality, the size of our DCT. Remember when we had the size of DFT with the circle convolution, like what's the size, like 256 point DFT. Now we have this 16 DCT or 8, which means 16 by 16, or 8 DCT means 8 by 8. How can we really choose between them? So there was this experiment, which is an interesting experiment. And this experiment is as follows. So in this experiment, there's something we call the rate distortion curve, right? RD curves, rate distortion curve. This rate distortion curve, basically it tells you as you really increase the distortion here, and you have the rate. Rate means how much you really add to it. So actually it's the other way around. This is distortion, this is the rate. So as you have very, very low rate, meaning that I can only afford the extreme case, like 100K or 1K, 1 kilobit per second. So my distortion will be very high. As I increase my rate, right? As I have like now I have 100 megabit per second. Then basically distortion is much less. I can really afford much more to stream in 1 second than before, so distortion is lower. All what we aim to is really to make this curve very close to the zero, because that means with a very slight increase in our rate, we drop distortion quite a bit, and that's what we want to do. And we'll talk about this in more detail later. So now for this experiment, simple experiment. Say, let's really apply. This is done for the Lima image. This is from really very, very old experiment, 15 years or 10, yeah, at least, yeah, maybe it's 10 years old, 11 years old. So if you have a particular Lima image, and then apply 8 by 8 blocks of DCT, and then keep only 25% and get rid of 75% of the remaining one. So now, instead of doing 8 by 8, do it for 2 by 2, 4 by 4, 8 by 8, 16 by 16, 32 by 32, 64 by 64, 128 by 128, 256 by 256, 512 by 512. And now what we are measuring is the root mean square error. Right? So what will be the mean square error in this each case? So what you do, to get an image in the first case, divide it into 2 by 2 blocks. For every 2 by 2, apply a 2 by 2 DCT. Keep 25%, which means what in this case? Keeping only the DC, throwing all the other 3 DCT coefficient every 2 by 2 block, and then do the inverse DCT, and then compare the 2 values in terms of root mean square error. So the error was here, right? So now go to the 4 by 4, and then do the same operation, but now you have 16 of these coefficients, right? Keep 25% of them, which is 4 of them. That means the DC, and 3 of the frequency, the low frequency coefficient, and the remaining 12, basically throw them away. And do the same thing, and then the error drops quite a bit to this value. We do the 8 by 8, we drop here. The 16 by 16, we drop here, we drop here. Then you keep doing that, and then as you can increase and increase, then there is kind of a saturation, and we'll talk in a minute about this slight increase in here. But for now, the whole what I want you to understand from this curve, that basically there is kind of an optimal windowing for the Lima image that will make this rule, which is keeping the 25%, throwing the 75%, works best, which is really in the circle in here. So around 16 by 16, 32 by 32 for this particular image, for this particular rule, that really gives you the smallest error, right? So that's basically kind of what I want to get from you. The second message is, if I do the same operation, but now I want to apply a different transform. So in one, I will apply the Fourier transform, discrete Fourier transform using FFT implementation. And then I'll apply the wavelet one. And we'll study this on next Tuesday, the wavelet Haar transform. And you can see in here, for the same image, same rule, keeping 25% of the coefficient for every block, throwing the remaining 75%, do the inverse, and so on. You can see that DC, the DCT, is giving you really the smallest, right, error. Compare that to FFT, and compare that to the wavelet R. So they all start from the same operation. So the DCT, you can see from this simple example, now you understand that the DCT is really closest to the origin here, even if you plot the rate distortion curve. So in this here, usually when you have the rate actually is some number that has bits per second, right? Or even better, you have bits per, in our language and in processing, we say bits per pixel. How many bits per pixel, right? Because we don't want to talk about streaming yet. So instead of saying what is the bits per pixel, in this experiment we said, okay, let's just forget about bits per pixel. Let's look at really what is really our block size. They are really related in the best way. So still, this is the rate. This is distortion. And then I want to be close to the zero. DCT is giving me the best rate distortion for this particular image, for this particular rule. And it's general, actually, it does, compared to the fast Fourier transform and the wavelet R transform. But we'll study more later on in terms of scalability. Why maybe DCT is not the best. Maybe R and wavelet transform is a good alternative, but also these for now, DCT give you the best rate distortion compared to the Fourier transform, compared to the wavelet transform for natural images. And now for the block size, there is as you really picking the right block size in the image with the same rule of throwing 25% or other rules, DCT maintain quite a bit of the energy, meaning that it does a much better compaction of the energy compared to other transform. And that's extremely important for natural images. And you can see it's really surprising how much difference in terms of the error and the quality between the fast Fourier transform or the discrete Fourier transform and the discrete cosine transform. And that's why I mentioned before, discrete cosine transform is very effective in natural images. And here is the a proof for that, for natural images. So this is a really very important subject, very important topic in the DCT. And in the new homework that you will be doing, will be busy with next week, we have some kind of coding experimentation. So you can really do this and observe what's really happening to your image as you do this process, this exact process. So again, Max will not be happy with our calculation here with the P and R, but yeah, he has the right to be unhappy. But yeah, I need to add the SSIM. So if you do the block size in here, so you have the original image on the left-hand side, you are zooming into one of those images that I showed you before. And here is basically a 2 by 2. You can see there's a pixelation effect happening. This is blockiness. Okay, I will fix that, Max. And then if you increase this to 4 by 4, this is the blockiness is more graceful. And then if you make it 8 by 8, then this blockiness is gone. So if you think about it, why do we have blockiness? So this blockiness is very important, and then maybe you have experienced this when you're looking at a streamed video online, either your TV or your laptop screen or even mobile. Sometimes you see there's this blockiness, and the blockiness is exactly this is the reason, because we are applying DCT and basically this is not the macro blocks. We'll look at macro blocks when we get to the standard for JPEG, but for now, just look at the blockiness effect. So when you have an 8 by 8 blocks, for example, in this specific case, then we are keeping only 25%. That means I'm replacing every 4 pixel values with the mean value, which is the DC, right? And here I'm replacing every 16 4 by 4, which is 16 pixels, with only basically the mean value plus 3 coefficients. So you can see the blockiness is a little bit more graceful than here, but still is very obvious. And here is much better because I'm really keeping 25% of the 60, 64. I don't know how much, like 18 something. coefficients. You can see, and as even reflecting that in terms of the quality. So now let's look at. Remember when in my examples before, when we talked about masking, and in the masking I said there was this red triangle. Let's really keep the first 10 coefficients, and then later I said let's keep the first 25 coefficients, and so on. So now there are certain specific algorithms that do this, and there are two of them that are really the most common ones. The first one is called zonal coding, which we did before. Zonal coding meaning that the location of the DCT coefficient in the block, meaning that is it on this, which is low frequency side, or on the high frequency side. The location of this coefficient will determine if we will or not, right? And the second one is the threshold coding, meaning that it doesn't matter what the location is. What really matters is the magnitude. So there's a threshold of the magnitude of the DCT coefficient. If a certain DCT coefficient is lower than a certain value, then I will zero it out. Like this is example here, this example here. If it's higher than a certain value, then I will keep it. And here is an example of what's happening. So there's a thresholding coding. This one is zonal coding in here. And in general, so this is on the left-hand side. This basically explains the difference between zonal coding and the threshold coding. So on the right-hand side, let me talk about this one here, and we'll talk more about this in coding. But usually we apply. So now you have to, even if you program this, if you try to code this, and you wanna, from a data structure point of view in programming, if your 64 coefficient, right? So I'm gonna write it as a with variation in frequency. Right? So now, if you write as a vector, do you wanna start from the DC and then you go row by row, or do you wanna go from the DC and go column by column? So the de facto, the standard way, it doesn't mean that it's the only correct way, but this is what really people agreed on in this community, is to do the zigzag. So you go from DC, go to the next coefficient, go to the next coefficient. As you are moving this way, every line you are going through, basically the frequency content in both directions is increasing until you hit basically the last one. So that's the whole idea. So you start DC, the next two coefficient, they have similar kind of in terms of contribution to frequency content, and the next three they are in the same 45 degree, the next 4 or 5, and so on. So this is the whole idea about the zigzag, and then that becomes our tracing. So what will happen is in the zonal coding, what will happen is you go through it zigzag wise, and then you stop where basically the zone is ended, meaning that after a certain number of coefficients, okay, everything else after that is just zero. In the thresholding, you go through each, the zigzag, and then you zero out anything below a certain threshold. So now, we don't really do it that way in the standard. What we do is this. What we do in here, we don't completely zero out. We don't really just pass things as they are. We apply kind of a quantization. So what this quantization means, where the coefficient is located, let me erase this. So in the first part in here, where the coefficient is located, it will determine the quantization coefficient, meaning that the easiest way to say the DC numbers, I will have 8 bits to represent the DC. The next ones, I will have 7 bits. The next coefficient, I will have 6 bits. The next one, I will have between 4, 5, and 4. Then 3 and 4. And so you can see in here, I will have these ones in here are 1, right? And then all of these are 0 bits. So this is one example, right? So now in this kind of representation, I I didn't really fix, because remember, if I do it this way, then I'm fixing things, right? I'm fixing what number of coefficients. If I'm doing it this way, then now I am taking into account both and the magnitude of DCT, because if I quantize a number that was here, right, with 1 bit, if it can, 1 bit can capture it, that's good. If it quantized to a 0, then basically that should not be decoded or encoded. So you can use in here, which is using is have the zone as well as the location, the magnitude, sorry, the location as well as the magnitude of every DCT coefficient in this case. So we'll revisit this. So now, if you look at the one that we use in JPEG for every 8x8 block, here is the standard quantization, where the input is on the x-axis and the output on the y-axis, and there is this parameter small c. See? This is c, 2c, 3c, and so on, right? So now our in JPEG, this c for the DC is 16, right? For the next one's 11. Compare the DC, which is 16, so 16, 32, and so on, and compare to 99. So for this coefficient in here, my quantizer is really map everything, right, between, well, that's 45, 47, and negative 47 to a 0. So you can imagine, basically, we have a very, very, very coarse quantizer for the high frequency content, and we have much more graceful or smoother quantization for the lower frequency ones. And now this is the one using JPEG. How did they come up with these numbers? It was experimental. It was an empirical study on some test images, and they come up with this matrix. Questions? Okay. So let's look at some examples using this. So now, what we did in this example, and you will play with these experiments in your next homework next week. So you have, what we have is 8x8 DCT blocks. We keep the first 25 DCT coefficient using exactly, and then each one of these, so for these 25 coefficient, we quantize them. So now I have a fixed quantizer for all 25 coefficient. For the sake of this experiment, I'm not applying this variations here, where I have every coefficient has a different quantizer. I'm applying the same quantization for all. So now, in this case, I have 100, and here I have 500, I have 300, I have 1000. So you can see basically as I go from for RBK, on top of that, I'm quantizing these 25 using this quantization, which is 100, meaning that for anything between negative 50 and 50, it will map to 0. So you can see in here, there is really a very drastic change in terms of quality as the quantization go between 100 to 300 and then 500 and 1000. So this just experiment to tell you how much there is constant compression, which is the trade-off between the rate or the rate, which is bits per pixel, the quality that you have in pixels. Okay, so now the next thing is I wanna. So DCT is really kind of the major block and major component in image compression, image coding, and video coding and video compression. But next, what I want to introduce is really an equivalent one, which is the discrete sine transform, and it showed up in recent video standards, compression standards. So if you look at if you remember how we got our discrete cosine transform, we obtained those by using certain extension of f of m and n. Now we have different extension. If you observe, you have this negative signs in here. So we have kind of an asymmetric extension happening. And here is basically what the extension looks like in this case. So I chose to have this extension here. Then I do the same shift as before for the axes. And now I have this extended f in this case. And then I do the same operation as before. If you notice what's the difference, the negative signs in this quadrant and the negative sign in the quadrant. That's really the major difference between the difference extension here and the ones in the DCT case. And now the same thing, the same operation as before. We apply the forward DFT definition. We split it into 4 regions based on the indices for the double summation. We calculate using each one by having a change of variable, recognizing this mirroring the 3 equations at the very beginning, and ending up with, for each one of them, in something with this double summation with f of m and n and complex exponents. So it's the same operation as before, really straightforward. And then using the important Euler's formula in this case. So the double summation limit, f of m and n, and then I have these exponents. And now I put these exponents next to each other. I observe basically they're nothing but sine times a sine. That's the difference. So now we have a different basis function. Is the sine is not really the cosine in this case. So you can think of this as the imaginary part of our Fourier transform or basis function. So now here are some examples for natural images. Apply DST. Same examples before. So I think that's, I don't wanna just side by side comparison. What is really the difference between the two? There's DCT and DST. Very rarely you can see a difference. So far, I would say is there a difference? Is really the DCT and DST, they are different component from the complex exponent expansion in the Fourier series. And in one is looking at the real part, and one is looking at the imaginary part. Both of them have very similar attitude in terms of how we can capture and compact the natural image. I'm hoping that we have time to talk about advanced video coding algorithms. That's when these T's start to show up, and we can really briefly talk about the advantage of DST over DCT in very specific components in there. I think that's about it for today. So we finished the DFT, we finished the DCT, DST, and then next we'll talk about wavelets and KLT, because really KLT is really the kind of major component in here. And then we'll study coding maybe in 3 lectures from today. We'll talk about image compression and the JPEG and then motion simulation in videos and optical flow and all that fun stuff. All right, I will stop here because I know in half an hour some of you maybe will take the exam. So good luck with the exam, and I hope any questions? Okay. All right. Take care. Good luck with the exam. I'll talk to you next week. Thank you. Bye-bye.